Hi, my name is Griffin, and I'm going to be sharing with you how we are utilizing a constrained Ensemble Kalman filter to determine the optimal oral glucose tolerance test duration for estimating insulin sensitivity. Now, insulin sensitivity is an important metabolic measurement that tells how effective insulin is at telling cells to take up glucose and to stop producing insulin. We use this measurement to determine information about metabolic diseases like diabetes and the correct treatment for those ailments. To get this measurement of insulin sensitivity, we need to fit the oral minimal model to glucose and insulin concentration data. We get that data through an oral glucose tolerance test, or OGTT. Now, previous studies have shown a duration dependence on SI for insulin-resistant individuals. So shorter OGTT data that maybe doesn't contain all of the features necessary doesn't give a good estimate for SI. We decided to try employing a constrained Ensemble Kalman filter to investigate this duration dependence, as well as to see how to choose the optimal OGTT duration. Now, an OGTT consists of an 8-hour fast, followed by a very sugary drink, and then successive measurements of the blood to determine glucose and insulin concentrations. This data was collected by our collaborators and gives the profile shown below for glucose and insulin concentrations. As you can see, the glucose concentration will rise after the sugary drink, followed by insulin, and then insulin will act on the glucose concentration to send it back down to baseline. We used this data to calculate 6-hour benchmark insulin sensitivity values that we could compare the constrained Ensemble Kalman filter forecasts against. Now, the model that we're using is the oral minimal model. This is a system of two nonlinear differential equations that represent glucose and insulin action dynamics. Now, we rescaled this model to include insulin sensitivity as an explicit parameter, and we're going to estimate insulin sensitivity as well as SG. In this model, we have RA. We're going to take that's the rate of appearance of the sugary drink glucose in the blood. We're going to take that to be the data that we got from our previous fit, and we are going to use the insulin measurements that we determined in the OGTT. We take this as a piecewise linear functional form. So we're going to take these three states and two parameters and apply it to the constrained Ensemble Kalman filter. Now, this is a technique that combines the data with the model to make a more refined model as well as better predictions. In this, we're going to have a certain number of vectors of these three states and two parameters, and we're going to propagate them between time points using the oral minimal model. At these time points, the ensemble is going to represent the variability in the system and will update based off of an optimally weighted difference in the forecast and the difference in the measurement with the forecasted measurement to readjust the states and parameters to more accurately represent the dynamics in the model. We use this constrained Ensemble Kalman filter to dynamically estimate the parameters of insulin sensitivity and SG by fitting the oral minimal model to this OGTT data. So what does this application look like? Here we have a representative individual where we see the ensembles in blue propagating between time points. Now, these ensemble forecasts don't necessarily line up with the measurement, and we can see the update in the transition from these red stars to these black circles. Now, that update means that the data assimilation is working. We can see this process is happening. For insulin, we don't see the same situation since the measurements and the forecasts are pretty much identical, but there's still an update. When we look at the parameters, though, for this individual, we can see that the insulin sensitivity measurement, this parameter, eventually becomes really, really close to its true or benchmark value. And this happens at about 150 minutes. Now, if we look at this individual, 150 minutes is where we get back to baseline level. It still goes lower, but that's an interesting relationship to be explored. So we do get insulin sensitivity convergence earlier than the 6 hours. And we see this in general for participants. We can get early convergence at 1 hour, 2 hours, but the best convergence happens at 6 hours. We see this relationship. We don't always get an individual converging, but we see a consistent relationship to more time, more data results in better SI estimation. Now, this indicates that we can get estimates of insulin sensitivity for shorter durations with the C and KF. However, the estimation is better with more data. In the future, we're planning to analyze more insulin sensitivity forecasts from these 1 hour and 2 hour thresholds to determine the key features that are driving the convergence. Now, I would like to thank all of the participants and their families, as well as the collaborators, and of course, my mentor, Dr. Cecilia Dennis-Ben. Thank you.